Let's take a look together at the remaining problems here in the 7.3 Achieve assignment. These, for the most part, are a little bit longer than the first 7. Number 8 here is asking us to integrate the integral 1 over x squared minus 81 quantity squared with respect to x. Okay, so the work I use to support my efforts in that problem is as follows. I have that integral, what I recognized in the denominator, that x squared minus 81, every single time I have a variable squared minus a constant squared, I'm going to say, let's let that variable equal a secant theta. So in this case, that's x squared minus a squared, so x is going to equal a secant theta, or 9 secant theta. Since a squared is 81, a is 9. So then after I do that, I can then say, well, dx is just the derivative of that. Derivative of secant is secant tangent, so I get 9 secant theta tangent theta with respect to theta. Now I go ahead and I show what that denominator is going to equal. X squared minus 81 quantity squared becomes 81 secant squared theta minus 81, and all of that group is squared. Well, I know the inside would factored be 81 times secant squared minus 1. Secant squared minus 1 is tangent squared, so the inside is 81 tangent squared, and then you have quantity squared. So I had to square 81. 81 squared is 65 61, then square tangent squared squared, I get the tangent to the 4th. After doing that, I can go back to my problem and say, well, my numerator is simply dx. That's my numerator. My denominator is that group squared, which I've already shown is 65 61 tangent to the 4th. So now when I bring this out, 9 over 65 61 reduced down to 1 over 729. The secant did not cancel in the numerator. I canceled the tangent to give me tangent cubed in the denominator, and I'm integrating this with respect to theta. As in a similar problem, I can't work with it in this format, but I'll just go ahead and create everything, or change everything to sines and cosines. Secant's 1 over cosine. You're dividing by tangent cubed. Tangent cubed is sine cubed over cosine cubed. If you divide by a fraction, you multiply by that fraction's reciprocal. That's where the cosine cubed over sine cubed came from. Now, from this step to this step, I'm simplifying that integral. I still leave the 1 over 729 out in front. 1 power of cosine reduced out of the numerator, and I have sine cubed in the denominator. Now, at that point, I was kind of left with thinking, well, that trick I used earlier is not going to help, because I can't let u equal the sine of theta and then du being the cosine of theta d theta, because the numerator would not cancel out. It's cosine squared. So instead, I just went ahead and said, well, I know cosine squared is 1 minus sine squared. And then I can say, well, I can then distribute this sine cubed into each term in the numerator. 1 over sine cubed is the reciprocal of sine cosecant cubed. And then sine to the 2nd over sine to the 3rd, that would be minus 1 over sine, which is minus the cosecant. 1 over sine is the cosecant. So I changed the cosine into 1 minus sine squared, then I distributed the denominator into each term in the numerator, and I split apart my integral. Now, the reason I did this is because now I can work with both of these two. Sadly, I work with those two using table formulas. There's really no nice way to work with the cosecant function. You might remember back in 7.2, I said we look for odd powers of sine, cosine, tangent, and cotangent. We look to attack even powers of secant and cosecant. Well, this is not an even power, so there's not a nice integration technique. So we go to our table formula. Now, you'll see in this step, I said now use tables formulas number 14 and 43. And I want to alert you to the fact, and this is not my mistake, it's a mistake of your book publisher. Number 43 has a typo in it. N should be 2. So it's also in the one that I posted online, because I'm just posting what the book has. This is the back of your book in it. And notice I said number 43. Let me scroll down to 43. You can see 43 right here. And it says the cosine cubed of u with respect to u is equal to negative 1 over n cosecant u cotangent u plus 1 over n natural log of cosecant u minus cotangent u. Please understand, in that problem, that n should be a 2. So that's minus 1/2 cosecant u cotangent 2 plus 1/2 the natural log of cosecant u minus cotangent u. It should be extremely similar to number 42. They've just made a mistake from 42 to 43. It should be very, very, very similar to 42 up there. The other formula that we're going to be using in this problem is number 14. You'll see 14 is the integral for your cosecant function up here. The integral of the cosecant function is your natural log of cosecant u minus cotangent u plus c. So now what you'll see on this problem is I just used those two formulas. First of all, the integral of the cosecant cubed theta with respect to theta is negative 1/2 cosecant theta cotangent theta plus 1/2 the natural log of cosecant minus cotangent inside the absolute value of that natural log. That's the first portion. And of course, I have the 1 over 729 times that, minus, and I ran out of room here, but I still think you can see what I did, minus 1 over 729 times the integral of the cosecant function. Well, that's what the number 14 told us, and that was the natural log of the cosecant of theta minus the cotangent of theta plus our constant of integration. Now, this would be the answer for the integral in terms of theta after using the table formulas, but I can't leave it in terms of theta, of course, so I can then go back to my original substitution where I can say, well, this is equivalent to x over 9 being the secant of theta. Use that to generate your table. We know secant's the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Hypotenuse is x, adjacent is 9. That means the other leg of your triangle has to be the square root of the hypotenuse squared minus the other leg squared, x squared minus 81. And every single solitary time, the expression from the original problem must pop up in your trig triangle, and it does. Now, I go to my integrations, to my integral solution. First thing I did is I factored out the negative 1/2 here. Then I had cosecant theta, cotangent theta, and I went ahead and distributed through and got this. Oh, actually, notice what I did. I said this term here would be plus 1 over 1458 natural log of cosecant minus cotangent, but then I have minus 1 over 729, the natural log of cosecant minus cotangent. These two are like terms. I've just combined their coefficients to get to this term down here of the minus 1 over 1458 natural log. So I combined this term and this term to get this term, plus my c. Now, getting it from terms of theta to terms of x, I use this trig triangle I was talking about. So I can say, well, now using that trig triangle, I can see that the cosecant of theta should be the reciprocal of sine. Remember, sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite, x over the root. That's where that came from. Cotangent, that's adjacent over opposite. That's 9 over that square root. Then we have minus 1 over 1458, the natural log of the cosecant minus the cotangent, those same two terms within the absolute value inside the natural log. Now, unlike another problem where we could just ignore the denominator of the natural log because it was just a constant, it's not the case here. Every part of this is going to have to be part of the answer because both your numerator and denominator inside that natural log are in terms of x. So the only thing I did here to simplify is I said, well, your first one, 9 over 1458 can reduce down to 1 over 162, and I'll have negative x divided by 162 times the group x squared minus 81. The square root times the square root is the group to the first power. Then I have minus 1 over 1458, the natural log, and I just went ahead, since I had a common denominator, write it as one fraction, x minus 9 over that common denominator of x squared minus 81, absolute value of that. Then we say plus or constant of integration, and you say, well, hey, that's a pretty cool problem. And if you're thinking that, you're thinking like me. And you'll notice Achieve liked it in that format right there. If I look at another question here, number 9, it's asking me to integrate with respect to x squared plus 16 to the 3rd power. And you'll see where I've put the answer in. Again, I want to show where that answer comes from. So looking at number 9 here with you, I have that integral dx over x squared plus 16 to the 3rd. As soon as I see x squared plus a squared, I know I'm going to let x equal a, which is 4 in this problem, tangent theta. Well, dx, 4 secant squared theta d theta. I need to show what x squared plus 16 cubed is. That's going to become x squared, which is 16 tangent squared theta, plus 16. Well, the inside of that, we know that that's going to be, and I should have a 3rd power on this group still. We know that that's going to be 16 times tangent squared theta plus 1. In other words, the inside is 16 secant squared theta. Well, 16 cubed, 16 times 16 times 16, 4,096. Secant squared cubed, because again, tangent squared plus 1 is secant squared cubed is secant to the 6th. I know that denominator is equal to this, so I replaced the denominator with that in the problem. And then the numerator dx, I already knew was 4 secant squared theta d theta. Now 4 over 4,096 reduces down to 1 over 1,024. And then I would have secant to the 4th left in the denominator. Rather than putting a secant to the 4th in the denominator, I went ahead and called it cosine to the 4th in the numerator. Now, ideally, what I would have loved to have done on this cosine to the 4th is use the trigonometry power reduction formula twice in order to simplify this expression. That doesn't work well in this problem just because trying to get it back in terms of x, having a multiples of angles makes it very difficult to deal with. So you really have no option other than to use number 45 from your table of integrals. Let me show that to you here. Table of integrals number 45 right here. Cosine to the nth power of u is equal to 1 over n cosine to the n minus 1 of the angle u times the sine of u plus n minus 1 over n times the integral of cosine to the n minus 2 of u du. Well, of course, if that's to the 4th, this is going to be 1/4 cosine cubed sine plus 3/4 the integral of cosine squared. So now please notice that's precisely what I did here. 1/4 cosine cubed theta sine theta plus 3/4 the integral of cosine to the n minus 2, 4 minus 2, cosine squared of theta d theta. Now, this part's already integrated. I'll use the power reduction formula on this part to make it easy to integrate. Cosine squared theta, I know is equal to 1/2 times the group 1 plus the cosine of twice the angle. Okay, so again, this first part already done. I distributed 1 over 1,024 times 1/4 to get 1 over 4,096 cosine cubed sine plus this 1/2 multiplied to the outside, and I already had a 3/4 out there. Oh, actually, I left the 1/2 on the inside for now. This is, I took that 1 over 1,024 times 3/4 to get to 3 over 4,096, and then that's times the integral of 1/2 times the group 1 plus the cosine of 2 theta. I could have went ahead and factored out the 1/2 in that step. I waited till the next step to do that. So that's where that 3 over 8192 came from. And then I'm integrating 1 with respect to theta, which is theta. And I'm integrating the cosine of 2 theta with respect to theta, which gives me the sine of 2 theta over 2. Yet again, though, you have to remember for me, we don't want that double angle because it makes it difficult to evaluate back into terms of x. So we know information about theta. So to get this back in terms of theta, we say, well, the sine of 2 theta is just 2 sine theta cosine theta. And then you'll see I've done that in the next step. The sine of 2 theta is 2 sine theta cosine theta. This 2 and the 2 in the denominator cancel. So then you get the sine theta cosine theta times the coefficient on that group, the 3 over 8,192. Everything else is the same as it was from the previous step. And you can say, well, we have our integral is equal to all of this with respect to theta, of course, plus our constant of integration. Now I need to take that gorgeous answer with respect to theta and get it back into terms of x. You use your trig triangle. We know that x is equal to 4 tangent theta, which means x over 4 is equal to the tangent of theta. I use that. Tangent of theta is opposite over adjacent. So opposite theta is x, adjacent to theta is 4. My hypotenuse has to be the square root of the legs squared, so I get x squared plus 16. And again, what's in the original problem must pop up in your trig triangle, and it does. So now I go in and I can say, well, my integral is 1 over 4,096 times the cosine cubed. Well, cosine is adjacent over hypotenuse. I take that fraction and I cube it. Times the sine. Well, that's opposite over hypotenuse. That's the x over that root. Plus 3 over 8192 times theta. Well, theta is right here. In order to solve for theta, you would just take the inverse tangent of both sides. So that's where I got the inverse tangent of x over 4. Plus 3 over 8192. Again, sine of theta is the opposite over hypotenuse, and cosine of theta adjacent over hypotenuse. That's where those two fractions came from, plus your constant of integration. At that point, it's just a matter of cleaning up the expression. What I did here is I realized 4 cubed was 64. 64 over 4,096 reduced down to 1 over 64. And then the only thing at that point I had left in the numerator, because that canceled out, was a factor of x. My denominator is going to be 64 times the square root raised to the 4th power. Here I have the square root to the 3rd times the square root to the 1st. A square root raised to the 4th power means you have the group to the 4 over 2 power, or that group squared. Now the next term I have 3 over 8192 inverse tangent x over 4. I didn't do anything to that part. The next one I reduced the 4 over 8192 down to 1 over 2048. The 3 didn't reduce with that, so I left it the numerator 3x over 2048, and then the 2 square roots multiply to give me that group to the 1st power plus your constant of integration. And when you check with what Achieve wanted for this problem, you can see that that was precisely the notation that I inputted in there, and it was absolutely fine. That was a fun question. Now, well, it was a fun question other than having to use the table formula for the cosine to the 4th. I'm not really a huge fan of that. Your next question here, number 10, actually pretty quick and easy. It's the integral of dx over 36 minus x squared to the 3 over 2 power. And soon as you see that a squared minus x squared, you can say, well, a is 6, a squared minus x squared, you let x equal a sine theta, in this case, 6 sine theta. Soon as I do that, I know that dx is 6 cosine theta d theta. And then the group in the denominator, 36 minus x squared, is going to be 36 minus 36 sine squared theta. The inside of this would simplify to be 36 times 1 minus sine squared, which is 36 cosine squared theta on the inside. Well, 36 to the 3 over 2 power, that's saying, okay, square root of 36 is 6, and then 6 to the 3rd power, 216. Square root of the cosine function would be, square root of cosine squared would be cosine, then cosine to the 3rd, you get your cosine cubed. So this denominator simplifies to be 216 cosine cubed theta. Now, once you get that beautiful denominator taken care of, you go back to your fraction and say, Well, your numerator here, the dx, it was 6 cosine theta d theta over that denominator of 216 cosine cubed. 6 over 216 will reduce down to 1 over 36. Now, you're going to have a cosine squared left in your denominator. You'll see I didn't write that because cosine squared in the denominator is the same thing as secant squared in the numerator. That makes it far easier to work with because you can say, well, hey, I know how to integrate secant squared because I remember from Calc 1, the derivative of tangent is secant squared. So the integral of secant squared with respect to theta is just the tangent of theta. I keep the 1 over 36 with it. I add my constant of integration. Now, that would be my final answer in terms of theta. I need the final answer in terms of x. So I refer to my trig triangle. That trig triangle is designed by understanding that x divided by 6 would have to equal the sine of theta. So theta is the angle in a right trig triangle in which the opposite side is x and the hypotenuse is 6. So opposite over hypotenuse. And then I can say, well, then the other side, the adjacent side, has to be the square root of the hypotenuse squared minus the other leg squared. And again, what's in the problem must pop up in your trig triangle. And it sure did. So now I go back up to my question, and it was 1 over 36 tangent theta. Tangent theta is opposite over adjacent. We get x over that square root. Add our constant of integration. All I did here was just rewrite it as one nice fraction, x over 36 on the square root of 36 minus x squared plus your constant of integration. And when we check that with what Achieve wanted, you can see absolutely exact same format, no problem. The last one here, the only really tricky part about this one is understanding that it makes the problem easier if you'll factor out the coefficient of the x squared term here first. If you don't factor it out, it makes it a more difficult problem. So you'll see that's the very first thing I did in my work. I have an ugly integral sign here. I had the integral of this function. I said, oh, okay, well, 16 in front of that x squared is going to make it a little bit hard to work with. So I recognized that I could say 16 times 7 is 112. So I could factor a square root of 16 out of this integral. And I can say, well, the square root of 16 is 4. So when I factor the square root of 16 out, it becomes a 4 on the outside. On the inside, 112 divided by 16 leaves me a 7. 16x squared divided by 16 obviously just leaves me an x squared. So now you have a squared plus x squared, where a is the square root of 7. So you can say, well, then I'm going to say let x equal the root of 7 tangent theta. Anytime you have a squared plus x squared, x is equal to a tangent theta. So dx is the derivative of that, the square root of 7 secant squared theta d theta. Now I need to figure out what that square root's going to give me when I put this into terms of theta. I can say, well, the square root of 7 plus x squared, that's going to give me the square root of 7 plus 7 tangent squared theta. And then on the inside of that square root, I could factor out a 7, and it would leave me 1 plus tangent squared, which I know is equal to secant squared. And the square root of secant squared is secant. So I get the square root of 7 comes out as a factor of the square root of 7. The square root of secant squared comes out as secant. Excuse me. Now I can go back into my problem and say, well, that square root is going to equal the square root of 7 secant theta. Dx is the square root of 7 secant squared d theta. So then I have the square root of 7 times the square root of 7. That's just 7. I'll factor out a 7 in this step. 4 times 7 gives me a 28 on the outside. So now I have 28 on the integral. On the inside, I'll have a secant cubed. And then I can say, well, all right, I would rather have an even power of secant if I were going to try to work this myself. Sadly, this is an odd power, which means we need to use our table of integrals to help out. And you'll see that I have that right here on the table of integrals. It's number 42, and I think we've talked about this one previously in this assignment. The integral of secant cubed is 1/2 secant tangent plus 1/2 the natural log of secant plus the tangent plus your constant of integration. So whenever I'm applying that formula to this problem, you'll see I did it right here. The 28 times secant cubed theta is 28 times 1/2 secant theta tangent theta plus 1/2 secant theta plus tangent theta inside of an absolute value plus your constant of integration. That's just directly from our table of integrals. Now this would be the answer if I wanted an answer in terms of theta. We don't. So now we use our substitution to help us put it back into terms of x. We know that x divided by the root of 7 would be the tangent of theta, which means that theta is an angle inside of a right triangle whose opposite side is x and whose adjacent side is the root of 7. That means your hypotenuse is the square root of this side squared plus this side squared, or 7 plus x squared. And again, your original expression should pop up in your trig triangle, and it sure did. Now, I go back to my problem, and I can say the integral is going to equal 28 times 1/2, 14. Secant of theta. Secant of theta, secant's again the reciprocal of cosine. Cosine would be adjacent over hypotenuse, so secant is hypotenuse over adjacent, square root of 7 plus x squared over the root of 7. Times tangent, which is opposite over adjacent, x over the root of 7, plus 28 times 1/2, again distributes to give me 14, natural log, and I would have secant plus tangent. I just went ahead and knew, well, it's just going to be these same two terms added, so they're going to have the common denominator of the root of 7, so I just said, well, it's this numerator plus that numerator all over 7. Now, the reason it's better to go ahead and write it like that is because then you know this could be simplified to be the natural log of the root of 7 plus x squared plus x minus the natural log of the root of 7. Once you write it like that, then you can say, well, that minus the natural log of 7 can be discarded because it's just a constant. It can get absorbed into the constant of integration, which again, that's something Achieve is wanting you to do. So from this step to this step, you'll notice I'm just getting rid of that. I'm absorbing that into the constant of integration. I can say, well, this is just 14 natural log of that numerator inside the absolute value. This over here, I said the root of 7 times the root of 7 is 7. 7 divides into 14 gives me a 2. I have 2x on that square root of 7 plus x squared plus the 14 natural log of that root of 7 plus x squared plus x plus your constant of integration. That's a pretty problem. Now, the only problem with these last several ones that we did in here, there were some fun aspects of them, but unfortunately, you do have to use your table of integrals on quite a few of them because there's just not a nice way to integrate an odd power of a secant function. So we have to rely on that table of integrals in that scenario. But you'll see when I entered this into Achieve for this problem, Achieve liked it just fine. So that finishes out this section. Hopefully this helps you out. This section usually gives students a little bit of stress, but I think you'll find it pretty fun once you get used to working with the problems. Next section coming up is 7.5, my absolute favorite of the semester, where we're integrating with partial fractions. Absolute glorious stuff that will involve some or quite a bit of algebra before we can do the calculus in the problems.